All right, let's do some word problems involving exponential functions. Okay, before we get into that though, we got to talk about e. All right, so we have this number e. It's approximately 2.71828, whole bunch of other stuff, goes on forever. It's named after this guy. Okay, here's his name up here. I want you to take a second, see if you can figure out how to pronounce this name. Did you pronounce it Euler? Because that's how it's pronounced. Okay, it's pronounced Euler. Greatest mathematician of all time, hands down. I would love to do an entire lesson on Euler as a person and as a mathematician. Super interesting. As we can see, he's got a pretty cool choice of headwear, and he gives a pretty mean stink eye. So this number e is named after him. It is very similar to pi in the fact that, it's irrational. Okay, goes on forever, doesn't repeat. There's no pattern to it. I think we scientists have it computed out to over 1 trillion digits at this point. It's actually really useful. In my opinion, it's more useful than pi. Okay, we see the number e come up all the time in science, in math, in finance. So it pops up in the weirdest places. I would love to do an entire lesson on e. Maybe we will one day. Maybe we will. Okay. It's often associated with the idea of natural growth. Okay, how things grow in nature. All right, and like I said, it is way cooler than pi. Okay, so when we use the letter e in this class, it is not a variable. Okay, it is not a variable. Keep that in mind. It represents a number, just like pi. Okay, where do you find it on your calculator if you're using a TI-84? Here it is right here. So second division. We'll bring it up in your calculator, and you can do e to some exponent by hitting second and this ln button. We'll learn a lot about ln later. We can also think of e as what you get when you take this function 1 plus 1 over n to the nth power, and as n grows really large, it approaches the number e. It approaches the number e. Seems a little bit arbitrary, a little bit random, but there's a reason for it. Okay, here we go. Let's do some word problems. So first off, we have to talk about two different types of interest. We have compound interest, just regular old compound interest, and we have continuous compound interest. Okay. So essentially the difference is with regular compound interest, you have some amount, some principal investment that you're starting with, and you earn interest on it, and that interest is calculated periodically. Okay, so every day or every month or every year. Okay, it's the rate that it is, the interest rate that is used is divided over some number of times, some period, and it's applied over a certain number of years. Whereas continuously compounded interest, instead of being compounded every day or every month or every week, it is compounded constantly, every tiny microsecond of a microsecond. All right, and the interesting thing about that is when you do that, you get a much simpler equation. Okay, some things to keep in mind here. So basically, you have a bunch of pieces that you're just going to plug in together. All right, you have your principal, that's your starting initial investment. You have your interest rate. All right, that's going to be a percent that you have to write as a decimal. You got to remember to write it as a decimal. Okay, n is the number of times it's compounded, right? And then with continuous, it's the same thing, except there's no n to worry about because it's compounded continuously, right? Let's do an example. So you invest $2,000 in an account that pays 3.17% annual interest. So first off, 2,000, that's our P. That's our starting initial investment. 3.17% is our interest rate, which we have to write as a decimal. Okay, remember for decimals, we move, or for percent to decimal, we move the decimal point over 2 places, 1, 2. How much money would you have if that interest was compounded monthly for 5 years? Or what if it was compounded continuously? So let's look at monthly first, and then we'll do continuous. Okay, so the first thing I'm going to do, I'm going to rewrite my formula. P, let's see, 1 plus R over N to the NT. Okay, so we have P is 2,000. We have R, which is what, 0.0317. We have N, the number of times it's compounded per year. Well, if it's compounded monthly, how many times is that per year? 12. Okay, and T, how many years? Well, that should be what? 5 years. So T is 5. Okay, we're going to take all of that and we're going to plug it in to our formula. So A equals P, 2,000. Now I don't need my comma here. One plus R, which is 0.0317 over N, which is 12, times NT, 12 times 5. 12 times 5 is 60, so you could just change it to a 60. Now, looking at this, this is definitely something that you would not be able to do by hand, very easily at least. So I would put this in some sort of calculator. I'm going to use Desmos because, you know, the nice thing about Desmos is we can type it exactly as it appears. And I'll show you what I mean right here. Okay, so I have Desmos up here. So I'm just going to first write out my formula. A equals P, 1 plus R over N to the NT. You don't have to worry about sliders. I like to write it out like this and then just fill it in as I go. So we have, let's see, A equals 2,000, 1 plus 0.0317 divided by 12 to the 12 times 5 is 60. And here's our answer. 2,343. So we have A equals 2,343, and let's round up to a certain number of cents, so, and 1 cent. Not bad. Made almost $350 in 5 years for doing nothing. We'll take it. Let's see what the difference is with continuous. So our continuous interest formula, A equals PE to the RT, PERT. Okay, all of these numbers are the same. So we'll fill them in. So A equals 2,000 e to the 0.0317 times t, which is 5. As you can see, it's much easier using the continuous formula. Let's see if it's much of a difference. You know, let's see if it's any more advantageous to use continuous interest. Okay, so we'll do 2,000 times e to the 0.0317. Oop. Times, come on, calculator, 5. And we got something very close. It looks like we only made about 49 cents more. So we did get something slightly different. 2,343, rounding to 50 cents. Okay. So is that much of a difference? No. Okay. So two things about this. On a short scale, a short time scale, you can use continuous interest a lot of the time as a good estimate for compound, or for compound not continuous interest. Okay. On a longer scale, over a much longer period of time, it turns out that continuous compound interest is going to outgrow the other model. So that's a fun fact. Okay, let's do another example now with just a kind of regular growth and decay model. So this is for pretty much any other growth or decay problem. So let's see. We have our guy, Randall Bobanderson. He is messing around and discovers a new type of bacteria in his gut flora, Cheesus burgeri. This bacteria has a growth rate of 65% per hour. So see that word rate? That's going to be our rate of change. Okay, that's our R. Okay. Randy swabs his gut, starts with a culture that 3 hours later shows approximately 25,000 bacteria. How many did Randy start the culture with? So I like this problem because we get to set up a growth model and we get to do a little solving. So instead of just plugging in, we're going to solve. Okay, let's think about what we know. We have a growth rate, which we have to write as a decimal, so 0.65. Okay, and we know that 3 hours later, so y when t is 3, okay, we can think of y as a function of time. Okay, is 25,000. So in other words, we have 25,000 bacteria when t is 3. So what we're solving for is we're solving for A, our initial value. Okay, I'm plugging in my R, and I know my t is 3. Okay, so what I'm going to do here is I want to solve for A, right? So let's try to simplify a little bit. So 1 plus 0.65, so that's just 1.65 cubed. Okay. In order to get A by itself, this 1.65 cubed, that's going to be some number, right? It's going to be some number. So we need to divide that away. Okay, we need to divide that away. So if I divide by 1.65 cubed on both sides, I'll have my starting value, my initial value, A. All right, let's pop this in Desmos, see what we get. So we'll do 25,000 divided by 1.65 to the third power. That gives us 65.29. Let's think. So we're counting bacteria, right? Are you going to count 0.29 of a bacteria? No. You're just going to round. So we're just going to round to the nearest whole number, or 5565. So this would be 5,565 equals A. So how many bacteria did he start with on his initial swab? He started with 5,565 bacteria.